Yeah, okay, great. Thank you for the introduction. I'm gonna talk about large charge expansion and beyond today, based on these 4 papers or more. So let's start. So interactions are interesting but difficult. I should have. Give me a second. I should have done this. Okay. Yeah. Anyway. Okay, interactions make physics interesting. The farther one goes away from the free field theory, the more interesting the physics becomes. Yeah, I wanted to, I didn't want to do swiping, but fine. Strong interactions are also unavoidable in physics. And typically, at low energies, theories become strongly coupled because of the RJ flow. However, strongly coupled field theories are usually hard to solve because of lack of perturbative expansion. And one usually needs some other assumption to track them, such as supersymmetry, integrability, etc. Okay. So here comes the rescue. So what if I tell you that one can still solve such theories without using those extra assumptions? What would you say? And it's true. Strongly coupled theory is kind of a limit sector in which it becomes solvable. And you know an example of this. One example is the sector of large spin. We know from analytic bootstrap, the CFTs usually become generalized free at large spin. Okay.
Sorry, Masataka,
Yes.
Can I interrupt with 2 things? One is that you know, the format of this particular seminar series is we ask a lot of questions.
Please.
And let me start then by asking if you could define what you mean by solvable.
Okay.
So a CFT, for example, I would consider a CFT solvable if I can compute all the correlation functions to any order I want.
So the way in which it becomes solvable at large spin is that it's even less solvable than you imagine. I mean, you can only compute for example, the operator dimension of double trace operators as an expansion in 1 over L, and that's all you can do. So that's what I mean by solvable. It's less solvable than what you said. You can't write down all the physical quantities related to, physical quantities, even if you go to large spin.
Okay.
And for large charge too, you can only compute the OP coefficients or the operator dimension or endpoint function, including large charge operators. But I'm going to explain that later.
Okay, good. Thank you.
Great. So yeah, do ask me lots of questions. And okay. So another example, which we're going to discuss today, is a sector of large global charge. So by solvable, I mean, okay, in this case, the sector becomes semi-classical, as we will see later. That's what I mean. Okay. If you give me 1 second, I can, give me a second. Yeah, okay. Okay, great. Okay. Now, so we will see that there is an effective field description in the inverse charge expansion. And one example we're going to study is the Wilson-Fisher fixed point. So let's start from the simplest example, which we can study at large charge. And we also concentrate on CFTs from now on, okay? And we consider the 3-dimensional Wilson-Fisher fixed point and try to compute the operator dimension phi q for q much greater than 1. So that's what we're going to do. And that's what I said by solvable. We can, I just meant that you can compute the operator dimension of this particular operator or the OP coefficients thereof. So as you know, the UV Lagrangian of the Wilson-Fisher fixed point is given by such a phi-4 interaction. And in the IR fixed point, which you m squared to 0 or something. I mean, you know, if it's in the sphere, you know, turn on conformal coupling. Anyway, but anyway, the lambda is order 1, so it's strongly coupled. So there is a key ingredient to if you want to compute the operator dimension of phi to the q here, because it's a CFT. You can talk about state operator correspondence. Now that we consider CFT, we can use state operator correspondence to compute a dimension of phi to the q. And the way you do it is that phi q is the lowest operator of charge q. So this corresponds to the ground state energy of charge q on S2 cross R with radius 1. Okay, no questions? Okay, this is important. Also, in order to compute the ground state energy of charge q, we can use the Grand-canonical ensemble. So Grand-canonical ensemble is defined like this. Z is defined like exponential minus beta times h minus mu q using chemical potential. And because we put the theory on S2 cross R, and we turn on the temperature, and this becomes S1 with radius is beta, and you're computing this quantity.
Can I ask one more question?
Yes.
So just to go back one slide. Yeah, there. So, okay, I'm computing the lowest dimension operator for a fixed Q, right? Mm-hmm. So, for example, can I think about it this way? Mm-hmm. Can I think about it as I have some set of operators, right? Mm-hmm. And I organize them by operator dimension. Mm-hmm. Okay. And I fix the charge, and mm-hmm. then I can kind of organize my operator dimension in some sense, let's say, is proportional to how heavy the operator is.
Yes.
Right. Okay. So then I'm asking for the lowest operator. I'm asking for the operator the lowest dimension for a fixed Q. Mm-hmm. So in some sense, this is a little bit like I have some, so I have some arbitrary set of states mm-hmm. in my theory, and if I look for the lowest mass state for a fixed charge, mm-hmm, mm-hmm. then by the Olive-Witten theorem, that's kind of looking at the supersymmetric point. Is that?
Yes. So when you have supersymmetry, yes, that's what you. Yeah, exactly. So exactly. So when you have supersymmetry and the lowest operator is protected by SUSY, I think that's what Witten index does.
Correct.
So here we're talking about non-supersymmetric theories, but we can also talk about supersymmetric theories. If you like, after I finish the talk, I can, I can explain it to you later. Although I haven't prepared, I think I can prepare. I can present it to you after I give the talk. But so there, it's exactly what you said. One is computing. One is in effect computing the large Q expansion of the Witten index, sort of.
Okay. Okay. Good. I mean, I guess I meant in a non-supersymmetric theory, the statement of the Witten-Olive theorem is that.
Witten-Olive. Okay.
Yeah. If I have BPS, if I have a BPS limit in the theory, mm-hmm. then I can always extend the algebra to a SUSY algebra, right? Mm-hmm. Mm-hmm. Okay. And so if I can find this lowest dimension operator for a fixed Q, then there is a BPS. These are BPS operators.
No. Sorry. Sorry. No. So in this case, so you're talking about non-supersymmetric theory.
Say.
So if you're talking about O.T. Wilson-Fisher fixed point, this is not like I don't think this is in any way.
I don't think it necessarily implies I don't think it necessarily means supersymmetric. I'm asking if I'm allowed to think about it as looking for a BPS object in the theory.
Okay. I see. No, I get it. So okay. First of all, I don't know the answer to this question, but I think if you go to the dual picture using ADA-CFT, this is similar to looking for the extremal object in gravity.
Okay. All right. Thanks.
But that, there is a proposal like that, but I'm not sure if it's perfectly correct because the ground state degeneracy at large Q is 1 here. You know, there is only one operator of the lowest charge, while black holes, you know, charged black holes have lots of entropy. So to be honest, I don't know how to answer this question.
No worries.
Okay. So give me a second. I think so. I should be using this one instead. Okay. Because I have to swipe every time. Okay, this is much better. Okay, so phi q is the lowest operator dimension, lowest operator charge q, and this corresponds to the ground state energy, as I explained, a charge q on S2 cross R. That's the state operator correspondence, and in order to compute such a ground state energy, we can use the Grand-canonical ensemble. And then I admit that it's the way you compute. I mean, the Witten index, for example, is you know, exactly the Grand-canonical ensemble. So there might be a way in which we can relate these two, but I don't know the answer to this. But anyway, we can use the Grand-canonical ensemble. This trace can be computed using this path integral here. Path integral of the action minus mu to the q. And as you well know, q can be computed by differentiating log z with respect to mu, and computing E can be done by taking a derivative with respect to beta of log z, right? And we were interested in the theory on S2 cross R, so we take the low temperature limit by taking beta to be infinity. And there you have the relation that the Grand-canonical free energy is similar to a partial derivative of log z over in terms of beta, okay? So you simply evaluate the Grand-canonical free energy to get E minus mu q. And you take the Legendre transformation to get the E, the expression of V in terms of q. Clear? Is this all clear? I guess so. So the other key ingredient is the saddle point analysis. So we can go on, evaluate the path integral and compute the Grand-canonical partition function, again, which is defined by this path integral, okay? It's a path integral of the action minus mu to the q, and the integral is over S1 cross S2 cross S1, sorry. And you take S1 to R by taking beta to infinity. So rho here is the charge density. And the new Lagrangian contains a chemical potential like this, and you compute the saddle point of this Lagrangian and expand around it to get the physical quantity. And you can immediately see that the saddle point of this Lagrangian is like constant times exponential I mu t. You can just compute it to see that, or I can explain it to you because you can define a new field. Large phi is equal to exponential I mu t phi or something, and the action with chemical potential becomes the usual Mexican hot potential. So it's clear that the VEV of phi is constant and has a dimensionful VEV, and by going back to phi, the small phi, you get the A times exponential I mu t. So it's a helical solution, and the A is large when mu is large. You know, so when I say mu is large, this is compared to the ion scale, but we said R equals to 1, so mu equals to mu is large. The statement that mu is large makes sense. Anyway, so it's a saddle point analysis, but okay, we're free to use saddle point analysis. We never know the loop corrections are suppressed, but it is valid. The loop corrections are actually suppressed, and use a modified Lagrangian, then the saddle point is this. So when mu and A is large, the action itself becomes large. So the saddle point approximation is valid when the loop corrections are suppressed. So I think this point people have never thought about. If you include the chemical potential and go to the saddle point, it's when you take the chemical potential to large, the saddle point approximation is valid. People have never thought about it back then. So a plot twist is that we use effective field theory to analyze this. So we can go on and actually compute the classical action and the one loop corrections and two loop corrections and so on, if it was a weakly coupled theory, using for example, one loop correction is suppressed by a factor of G, factor of the coupling, two loop coupling squared and stuff like that. And in fact, we can do this in the epsilon expansion because lambda to the FIFO theory, lambda is of order epsilon. So you can do it in the epsilon expansion, but in the absence of such a weak coupling parameter, we can just use effective field theory around the saddle point. Since it's because it's a valid saddle point, you can use you can write down the effective field theory around it. And writing effective field theory is all about symmetry breaking pattern and the massless modes created by the saddle point, created by the symmetry breaking. And to make use of all the underlying symmetries, let's first forget about the chemical potential term, which is like mu to the mu times rho, because this can be added later by hand. So we're interested in the symmetry of the original Lagrangian lambda, which is the Lagrangian for the Wilson-Fisher fixed point. Okay. Do you have any questions? No. So now we decided to write down the effective field theory of our original action, this, around the saddle point like this, A times exponential I mu t. And this is a weird saddle point. This breaks the time translational symmetry spontaneously. This breaks Lorentz symmetry spontaneously. This also breaks conformal symmetry spontaneously, but it doesn't matter. The symmetry of the underlying theory is conformal invariance and global symmetry. And by spontaneous symmetry breaking from phi 0 is equal to the helical solution, there appears only one number-Goldstone boson from breaking O2. Even though you break other symmetries because they commute with the global symmetry. I mean, one is actually breaking global, not the global symmetry, but the global symmetry combined with the time translation. So I mean, because of the complicated non-abelianness of the original symmetry, you actually only need one number-Goldstone boson in this system. Another symmetry, yeah, okay, I said it, but other symmetry gets broken too, but there is still one number-Goldstone boson. It's a bit weird because you broke Lorentz symmetry spontaneously too. It creates a weird situation. So now that we have one massless mode, chi is the angular mode. Again, phi is equal to A times exponential I chi. And our job is to write down the effective field theory consistent with all the symmetries of the original theory. And the building block is easy because it's only partial chi. Because the chi transforms non-linearly as chi goes to chi plus c. Okay, so you can hit derivative to cancel it. In order to realize conformal invariance non-linearly, we also usually couple the theory with dilaton, which is the radial field. And we can do this honestly, but this time the master A is of order partial chi. By just dimensional analysis. So we integrate this out. But by the way, dilaton is usually massless, but this time the other broken generator does not commute the dilatation, and this makes the dilaton massive. And the rules for effective operator is to build with partial chi, that absolute value of partial chi can appear in the denominator. Usually, building effective field theory does not want you to put any operators in the denominator, but because it's the master of the heavy mode, you can put it in the denominator, the partial chi, not the other operators. Good? I have a feeling that I'm saying something complicated, but if you get it, it's great. Absolutely no questions? Absolutely? Okay. So we can now sort all effective operators according to the mu scale. Mu was partial chi. Because chi was like mu t, partial 0 chi is mu. Oh, so I will just give you the result of the sorting all effective operators, which is like this. So the first term is mu to the cubed because partial chi is of order mu. Partial chi is of order mu, so this is of order mu. The Ricci curvature is the Ricci curvature from the underlying geometry, and you have two undetermined coefficients because it's the Wilsonian action, and you have no way to determine the coefficients in writing down the effective field theory. Also, you can see that there are no operators of at order 1, for example. And the subleading operator is q to the minus 1 over 2. Sorry, I mean order 1 over mu. Okay. From Noether theorem, we have mu is equal to O to the square root of q. So this is, the first term is of order q to the 3 halves. The second is of order q to the half. As you might have noticed, the second term is only scale invariant, but not Wall invariant, because Ricci curvature is not covariant under Wall transformation. But one can complete it. And the completion is of lower ordering, so we don't care about it. I mean, this can be completed with something like this. But this is lower scaling. This is of order 1 over q, and this is of order square root of q. So this is much larger. You don't care about it. So anyway, so this is very weird, having a partial chi to the absolute value to the cube and stuff like that. But this is only meant to be used around the vacuums, which is chi 0 is equal to mu t. So the singularity is not a problem. No terms is available at order 1. This is going to be important later. So again, our effective field theory is this, effective action is this, and our saddle point is chi 0 is equal to mu t, and we're meant to expand around it. So it's easy to see the classical contribution to the ground state energy. It's simply, I mean, this C and this C, these are not the same, but anyway, it doesn't matter, goes like C 3 halves times q to the 3 halves plus some coefficient times q to the 1 half and so on. This is the classical contribution from the saddle point. And the loop correction is again suppressed as the action itself is large of the saddle point. And one loop correction is of order 1. And since there are no effective operator there, the prediction gives a precise prediction as number, not as an undetermined coefficient in the EFT. There is no way to change the quantum correction using these undetermined coefficients. So the one loop correction comes from the fluctuation term, which is defined to be chi is equal to mu t, which is the saddle point action plus the fluctuation. And the leading order term contains this fluctuation term. And by the way, you can see that the speed of the Goldstone boson chi fluctuation is 1 over square root of 2. This is not 1, but less than 1, because it's the consequence of Lorentz symmetry breaking and the underlying conformal invariance. So this number, 1 over square root of 2, is fixed by the requirement that the underlying theory is actually conformal. I will not explain you this, but it's true. And it's called the conformal bound of the non-relativistic Goldstone boson.
Can I ask a question?
Yes. Yes.
What would you expect to change if I have a non-relativistic theory?
Oh, yeah, right. That's important. So you mean, I think you mean non-relativistic theory where T goes like no. I mean the theory with Z equals to 2, right?
Yes.
So there it's give me a second. So it comes from I think it's 1 over t minus 1. Is that right? Yeah, I think it's 1 over d minus 1. Okay. So I think c squared, the speed of the Goldstone boson is 1 over d minus 1 in relativistic theory. And I think it's 1 over d, right? Because T has mass dimension 2, T has mass dimension 2. Yeah, so it's all because of dimensional analysis. T has mass dimension 2 and X has mass dimension 1. And it's the ratio between the number of space and number of time. So I would say this is 2 over d minus 1, if I'm getting it correctly.
Okay.
C squared.
But it's still doable for a non-relativistic theory, right? So you
it's definitely doable.
to get something for. Okay.
It's definitely doable. Yeah, okay. One can just write down the leading order effective action and expand around the saddle point, and then we can see some result.
Okay.
But I think it's 2 over d. D is the spatial dimension. 2 is the weight of the mass dimension of t in non-relativistic theory, Schrödinger system. Anyway, so again, our EFT was this, the saddle point was this, the helical solution, and we were computing the loop correction, okay? And the one loop correction comes from the fluctuation term like this, with speed of the Goldstone boson to be 1 over square root of 2 times the speed of light. So you can just sum up the 0 point energy using 0 point energy to get the one loop result. This is, of course, divergent. You need to regulate to renormalize. But on S2 cross R, there is a convenient regularization, which is zeta function regularization, and you get some finite number after all. And the 2 loop contribution is even more suppressed and starts at the q to the minus 3 halves and so on. I mean, 3 loop even further suppressed. Anyway, so what we did is the following. We used this effective field theory and expanded around this saddle point and get the classical contribution, which is this, and quantum correction, which is this. And because, so we set the radius of the underlying geometry to be 1 to compute the operator dimension of phi to the q. And the final result becomes this classical contribution plus this quantum correction and even further suppressed terms, okay? So this is the final result for the dimension of phi to the q. And unfortunately, because we used effective field theory, these undetermined coefficients are still there. So these can be determined using weak coupling expansion or numerical simulations or something like that. Okay, so this is the final result. And the only assumption we used, of course, I told you that we start from O2 Wilson-Fisher fixed point, but the only assumption we actually used is a symmetry breaking pattern. So the massless modes. So the effective field theory is all the same for other theories, but this specific symmetry breaking pattern at finite chemical potential. They of course have different undetermined coefficients and so on, but because the quantum corrections are not corrected by these undetermined coefficient, this minus 0.094 is all the same for such theories. So if you have some other theory whose symmetry breaking pattern is O2 to nothing at finite chemical potential, you expect this to as the operator dimension a charge q, lowest operator dimension at charge q. And there are actually an infinite number of such examples, which is the CPN-1 model, large monopole number. You can actually compute using large N expansion and check this result. Anyway, we call this the large charge universality when multiple different theories behave in the same way at large charge because of the same symmetry breaking pattern, finite chemical potential. Okay. So let's show you some fun plots. We can also compare this with Monte Carlo simulations. And people computed the lowest operator dimension at fixed charges of O2 Wilson-Fisher fixed point up to J is equal to like 12. And see if our formula fits well. I mean, J is equal to 12 is not really big, but the results suggested a remarkable fit even down to J equals to 1. Q equals to 1. I'm sorry, I've been using. So look at this result. I mean, Monte Carlo data is shown in this block. The set using this function is shown in the line, and you can actually see that it goes all the way down to q equals to 1. So it's really amazing how this formula fits well for small charge. The mechanism, I don't know, but it actually fits very well. And this lets me to think that the large charge expansion is actually a natural parameter to study strongly coupled theory. Well, it's just my feeling, but so anyway, this result is weird though. So we've seen that delta of q goes like q to the 3 halves, but why is the operator dimension not proportional to q? If we used Feynman diagrams, we should get delta q is equal to q plus corrections. And in particular, we can do the same thing for in general Wilson-Fisher fixed point in general dimension, and we would have gotten delta q is equal to d over d minus 1. And that d equals to 4, we should get q equals to 4 over 3. And this is weird, because the Wilson-Fisher fixed point is a free theory at d equals to 4. So there are multiple weird things in this result, but they're all not weird though. Imagine computing this using Feynman diagrams. Let's say, well, the weak coupling parameter G, and G is the strength of the two-body interaction. And there are Q particles here because we're computing the operator dimension of phi to the Q. And G to the K minus 1, order of G to the K minus 1 correction to the leading formula comes from K body interactions between them. For example, two-body interactions give you order G result, three-body interaction, because the three-body interaction gives you order G squared and stuff. And the way to pair K particles up inside a total of Q particles is given by Q choose K. So this is roughly Q to the K. So in total, the correction will go as this, G to the K minus 1 to Q to the K. Anyway, what I mean is that the actual expansion parameter is not G in this expression, in the Feynman diagram computation, but actually G times Q. And because we're doing Feynman diagram computations, if we did Feynman diagram computations, such a result can only capture the regime GQ is much less than 1. While our effective field theory capture the regime GQ much greater than 1. So there is no contradiction between the two results. Even more, we can explicitly compute this and show that the crossover between the two behavior, if you go back to our Grand-canonical ensemble, and if you compute the subtle point of this in the epsilon expansion, as well as loop corrections around it, I will not show you the result, but it's just classical field theory, and you can actually show that the energy crossover shows the crossover from delta Q is about Q to Q to the 4 over 3 when epsilon Q is much smaller or much larger than 1. And you can also compute loop corrections, and this is epsilon K to log Q to the K. So when epsilon Q is much larger than 1, and this will modify the result from the 4 over 3 to D over D minus 1, the scaling of Q to fit with the dimensional analysis. Okay, I mean, this is what I mean. So this is the loop correction. This you can get from classical analysis. Anyway, so there's nothing wrong about the result, and it's actually being checked using epsilon expansion. Okay, so it's half of the talk. Any questions? Anything? Fine.
Yeah, I have a question. Sorry.
Please.
I'm not sure whether you're getting to this or not. So this is the O2 Wilson-Fisher.
Mm-hmm.
Okay. So suppose I have a theory that has an n expansion.
Mm-hmm. Large n.
Sorry.
Large n.
Yeah. Okay, so my question is, do you know what happens if you take both n and q large, but let's say you have a new expansion parameter, some q over n.
Yes.
Okay. All right.
Very good question. For ON model, the expansion parameter is actually q over n.
Okay.
So the similar thing happens here. So when n is much larger than q, it goes like delta is about q over n, or some n scaling. So when n is much smaller than q, delta goes like q over n to the 3/2 in 3 dimensions. So again, it shows a crossover of operator dimension because n suppresses the coupling constant. Okay. But for the CPN model, this does not happen because n does not suppress the coupling constant, and it actually works as q times n.
I see.
So it's always this. There is no crossover. Even if you take n to be much larger than q, the operator dimension of the state with q monopole is still q to the 3/2.
Why is that? Well, I mean, why is this the case for CPN? And can you think of another example that would disambiguate? I mean, so okay, when n equals 1, admittedly, this is not in your parameter range, but when n equals 1, the CP1 model and the O3, the CP1 model is the O3 model, right?
Yes.
Right. So is there some divergence at large n between the behavior of the scaling dimensions in these theories?
No. So again, what I mean is the following. I think I didn't make myself clear. So I'm just saying that for the CPN model, the operator dimension can be computed, but I think it goes like this. Sorry, I'm forgetting all the coefficients. No. What I'm doing? What am I doing? This plus something like this. This is what I mean. You can actually compute them.
Right, but
by the ordinary.
But the leading behavior is still not like q over n, right? It doesn't scale like q over n. It scales like or q over n to some power. It scales like the product of q and n.
Right. So I think this is the correct result. I said it works like this, but it's not.
Okay, so it goes like nq to the 3/2. Okay.
And I can't quite remember the reason for this. There was an interpretation of the result. It's roughly because I think it's roughly because in the loop computation, if you do loop computation, in the loop because n particles run in the loop, I think this is why. So this doesn't help suppress the loop correction if you.
I see.
That's if you do ordinary Feynman diagram. That's the reason. But for ON, it's different because you can see that the fixed point value of the coupling constant gets suppressed at 1 over n. So that's the reason. That's okay. What I think is the reason.
Okay. Thanks.
Yeah. So it's case by case. So sometimes there is no crossover. Sometimes there is crossover. And yeah, that's that. So there are possible generalizations in a number of ways. So for example, we can apply this to Soucy theories as moduli space of vacua, and then we'll have BPS states, BPS operators of large Island charge. And the lowest operator dimension, of course, at large charge is linear in null because it's BPS. Second, the effective field theory term is constrained a lot more because of the larger symmetry, because of larger SUSY, and it's cleaner in a sense. Or completely differently, you can generalize the global symmetry itself. You can start from O4 as a start. And the latter is what we're going to discuss from now on. The only question is it interesting? I mean, usually making O2 model to O4 is not very interesting, right? But that's what we're going to do. So let's study the O4 Wilson-Fisher theory in 3 dimensions. And O4 is like SU2 cross SU2, so it's rank 2. And there are 2 charges to take large. And for convenience, we write everything using the SU2 doublet Q instead of 4 real scalars. And building, if effective field theory is easy, you can follow the previous procedure for the O2 model, and we give VEV to the radial. So let's divide Q into A times Q. A is the radial field, and we give VEV to it, left with the number Goldstone mode Q, where it's the cos. It lives on the coset. And using Q, the leading order effective field theory is simply the same drop height to the cubed action. Okay. So we have this effective field theory, and we want to know the saddle point configuration of fixed charge Q1 and Q2 much greater than 1. And Q1 acts as, so Q1, Q2, acts as U1 on Q1, and Q2 acts as U1 on Q2. Q is the charge, global charge. So to simplify the analysis, we put the sphere in the torus, not the sphere, but it's still still interesting, with coordinate x and y. The ansatz to such a configuration is such a saddle point configuration is this. So you have exponential I mu t factor here still, but I've set the spatial dependence on the configuration. And it depends on spatial coordinate, as we will see. If you had written down the homogeneous configuration, you wouldn't find the solution to the equation of motion. Anyway, so we have effective field theory and the ansatz to the saddle point like this. And for the O2 model, the homogeneity was an ansatz, which was later checked as a posteriori. This time, such an assumption is invalid again. And that this only depends on one coordinate x is also an assumption, and we will check this later by finding a solution to the equation of motion. So let's solve the saddle point configuration by using this ansatz in the effective field theory. You can, it's hard, but you can solve this and get the solution like this. So sine of px is proportional to the Jacobi elliptic function. It's a periodic function with period L. L is still indeterminate, but any L is as good a solution as anything else. Okay, and P0 here is the maximum of Px. So sine P0 is the maximum of sine Px. That's what I should say. So you have the configuration like this, and this is P0, for example. It's an increasing function, ρ1 over ρ2. Rho is the charge density, so Q1 over Q2, it's the same as Q1 over Q2. This means that when you take Q1 to be 0 and Q2 to be large, so if you only rotate one charge, you get the homogeneous solution because P0 goes to 0 in this limit. We recover homogeneous solution as an O2 Wilson-Fisher fixed point. And that it's the most inhomogeneous when ρ1 is equal to ρ2. So if you excite the 2 charges by the same amount and take them large, it's the most inhomogeneous. Anyway, so we found the saddle point configuration, this, and you can compute the energy of this configuration. I'm not going to show you how we compute it because it's very technical, but we get the following result. So the energy density is proportional to the charge density to the three halves, as in O2 Wilson-Fisher fixed point, but there is a correction to it. What's this? Okay, correction to this, like going like this. So it's proportional to 1 over charge to square root of charge, and it depends on the period of the solution. And A is some positive constant. Anyway, this means that larger L is favorable as a ground state solution. So for the if you're looking for the ground state solution on the torus with fixed charge, L coincides with the larger period of the torus. I mean, if you have a torus like this is L2 and this is L1. You have a homogeneity on this direction, x-axis. So anyway, we found that the ground state at large Q1 and Q2, none of which are 0, leads to a spatially inhomogeneous ground state. Okay, not the homogeneous ground state as we saw in O2 Wilson-Fisher fixed point. Okay. So I'm gonna summarize, but any questions? Okay. So as a summary, a sector at large charge becomes semi-classical and solvable, and we can use effective field theory to explicitly see this. And many interesting phases are realized at large global charge according to the symmetry breaking pattern. So the O2 Wilson-Fisher fixed point realized the simple fluid, but O4 Wilson-Fisher fixed point realized the spatially inhomogeneous superfluid when we excite two charges at the same time. So it breaks the translational symmetry of the spatial slice as well as the original global symmetry. So, but by the way, so this spatially homogeneous superfluid is called the FFLO phase in condensed matter physics. I think this is important in studying the organic superconductors. This was first discovered in, I think, non-relativistic CFT, which is called the Fermi, fermion unitarity. So for fermion unitarity, you have two species of fermions, so you can excite two different chemical potentials for the two species of fermions, upspin and downspin, and then that's equivalent to having two different charge configurations to the charge. So this is the same thing as the FFLO phase in condensed matter physics. Anyway, so we have additional Goldstone boson for inhomogeneity. And how should we count the number of low energy degrees of freedom then? So we have only 3 low energy degrees of freedom, we should check how to match number of low energy degrees of freedom with number of broken generators. Because it's the non-relativistic Goldstone boson, the counting is a bit weird here. Also, we should do complete classification of effective field theory operators to the O4 theory. Because the one suppressed for O2 Wilson-Fisher fixed point might not be suppressed for O4. For example, if you imagine an operator, partial mu, partial chi. In the O2 case, chi was mu t, right? So upon hitting with chi 0, you get mu already. You get constant already, so it's 0. It's suppressed as a classical solution. If you plug in classical solution to it, but because chi is like exponential I mu 1t, I mu 2t, sine px, cosine px. Hitting with one derivative does not kill chi. Classical partial nu chi evaluated with a classical solution is not 0, but some finite amount. So you should check, one should check, one should really check the subleading corrections to this. Also, one can study O4 in the Wilson-Fisher fixed point in the epsilon expansion. And one can study other large charge universality classes. For example, if you study Chern-Simons matter theory, this realizes the homogeneous but anisotropic superfluid. And this information should be the same across duality, so it's maybe useful for the check of duality. And the other thing would be to study d equals to 2, like O4 sigma model, and use integrability to constrain the coefficients in front of those effective operators. So that's it. Finished. Yes.
Great. Well, thank you very much. Any questions? Anyone? Okay, so I have a question. What would you say is, okay, so we've learned, we've learned a lot from the large N expansion. We've learned that if you organize your perturbation series in 1 over N, then going to large N gives you a new view on the theory, right? And your statement here is that there's a similar organizational paradigm for large charge operators.
Mm-hmm.
And you're not distinguishing what type of charge you're talking about. So R charge, electric charge, magnetic charge, they're all the same to you.
Mm-hmm.
And so double scaling limits are kind of equally good in this case as well, right? So normally we would take, let's say, G Yang-Mills, and we can scale, we can scale G Yang-Mills times N, or G Yang-Mills squared N, and give us a new parameter. And one of the things that this has allowed us to do is something like the BMN limit, for example, where we can actually probe stringy effects. Do you see something similar? So I have two questions. One is, do you see something similar here? And then the second question is, how do I understand? So let's take the ON model.
Mm-hmm.
Right? If I go to the large N limit, then I expect that this theory will become. If I go to the large N limit, I would expect that this theory basically goes to the gravitational theory, and the gravitational dual of this is Vasiliev.
Yeah.
How do I understand the large Q limit in large N? So if I have these two parameters, Q and N,
mm-hmm, mm-hmm.
and if I take the one limit first and then I take the second limit, how do I understand that in the Vasiliev theory?
That's a very tough question, actually. So I don't even know what's the dual of the 5Q operator in Vasiliev theory. But what's the I don't think I have any answer to this question. It's too tough.
No. No worries.
It's
I guess what you think about.
Yeah, we're gonna think about it. So.
And then the second question is, another question that I have is, so you've given two kind of archetypical examples of the ON model and the CPN model.
Mm-hmm.
And the one behaves like a vector, and the other one, well, actually both of those behave like vector theories, actually, right? So they're vector models. But I could generalize the CPN model to a Grassmannian sigma model, for example.
Mm-hmm. Mm-hmm.
Yeah. So GRMN, M/N, or whatever the case. And that has a similar behavior to the CPN model.
Mm-hmm.
Right. In a sense, I go from complex lines through the origin to complex planes through the origin, and that's the generalization from CPN to GR. What happens in that case? Do you know? Do you have any intuition?
Never worked that out, but I suspect it's the same as CPN.
You see, the reason I picked this example is because the Grassmannian sigma model generalizes both ON and CPN. And so if you're finding, if you're finding particular behavior in CPN and another type of behavior in ON, maybe this Grassmannian is a way to disambiguate between the two.
That's really interesting. I don't know the answer, but I hope to, for example, find like if you take M to be much larger than Q. I mean, okay, there is a triple scaling M.
Exactly.
And yeah, that's really interesting.
Okay.
That's
good.
Cool. Really interesting. Thank you. That's cool.
Cool. Any other questions?
Did I make everything clear? I don't know. I actually tried a different type of explanation today. So
good. No, I really enjoyed it. Thank you. Very good. Okay, so if there aren't any more questions, let's thank Masataka again.
Thank you.
And thank you very much for the talk. The talk is recorded, and I'll upload it onto our YouTube channel, and you're welcome to view it when you can. And we should schedule a talk between you and me again shortly. But thank you very much for the talk.
Thank you very much.